Today we're going to talk about one of my favorite subjects. This is basically something I work a lot myself. And I think it's also one of the most useful models you will see in the class. And it's called the unit commitment problem. It's basically a generalization of the models we've seen so far, and it's as complicated as it will get as far as this course is concerned. So to motivate the model that we're going to look at, I'm going to talk to you a bit first about how control and operations are split into different parts. So there's the day-ahead part and the real-time part, and they do slightly different things. And the unit commitment problem is part of the day-ahead planning that takes place. And then I'm going to show you the model and some variants that have to do with uncertainty. Okay, day-ahead operations are performed somewhere between 24 and 36 hours before the beginning of the next day. And why would you think it's even necessary to do planning for the coming day? You could always make decisions in real time. So what is it about any system that makes you want to optimize in advance?
If you have renewable energy, no?
I could see it the moment it's being produced and
Then
balance.
if you have a storage system, you have to plan from the future consumption.
Right.
So
Storage is a good example. So anything basically in your model that creates time dependencies creates the need for planning, for looking ahead. Storage is a good example. Can you think of something else that has to do with thermal generators? I mentioned an example last week. There are nuclear units that need 1 week
that
notice.
generate the same level of power at any time.
Come again?
For the nuclear power plant, they generate the same level of power at any time.
If that were the only constraint, that would be fine. I mean, if I could immediately start them and get that level, that would be fine. It wouldn't create any time dependency. The problem is that to get them up and running, I need about a week's notice to get the whole thing started. So anytime you have time dependencies, that creates the need for planning. And typically the rule of thumb is if something takes you about, you look at how deep the time dependency goes, and that's approximately order of magnitude your planning horizon. For example, if it takes me a day to start a unit, I don't need to start planning for my system a week before or a month before. Order of magnitude, I need to start planning a day before. So you have minimum up and down times, and you have ramping rate constraints in conventional units that create these time dependencies. So what you want to do is, since to get at a certain level A of production, you need to decide about a day in advance, you run a unit commitment problem about 1 day in advance. Now, you don't have the full information for the next day, inevitably, because you're doing day-ahead planning. So as far as renewable energy supply is concerned and demand is concerned, you just use hourly forecasts for the next day. That's very different from what happens in real time. In real time, you've made a lot of decisions about a lot of your generators in the fleet. You have some really fast units that can start very fast or that can change their production very fast. And there you enter the domain of real-time balancing. In terms of thinking control theoretically, so in terms of your control action space, which problem has a larger control space? Where do you have more degrees of freedom? If I give you a mathematical description of the control set, of the action space for the day-ahead problem versus the real-time problem, which one would have a larger set of feasible decisions?
The great day-ahead.
The day-ahead. The day-ahead. So basically, a lot of the things you do in the day-ahead will fix your position in real time. So in the day-ahead, you have a range of possible production levels that you can achieve depending on the decisions you make. The uncertainty is going to evolve within another possible range. But as you're fixing decisions and approaching real time, so 1 hour in advance, you've fixed a lot of the decisions you can make. Actually, maybe your decisions have made you come over here. And now you're left with very few units that you need to adjust up and down. So your range of control actions can bring you here and here, but also you know the uncertainty much better. So the uncertainty will evolve within a smaller range of possible values. But that's the idea in control system operating, in power system operations, is that the further away you are from real time, the more freedom you have in terms of flexibility, and you gradually make commitments that reduce your flexibility until you reach real time where you're just running behind the wind forecast errors and the demand forecast errors. And so many power system operators have decided to literally break down operations in this way. We have day-ahead planning. You could then be doing replanning over and over until you're reaching real time, but there's this and some systems do that, but there's this standard separation of day-ahead unit commitment and the market around it, and then real time balancing and a market around it. So these are the two layers of the onion, if you will. Now, the day-ahead problem can be very large and very hard to solve. So this is an example of the largest model you will find out there. It's the Pennsylvania, Jersey, Maryland system. So that's the a good piece of the northeast United States. So you have 1,200 generators that submit these offers. These offers look a lot like what you submitted for your homework. So it's block bids of quantity and price. In addition, they also submit startup bids and no load cost. So these are the pieces of information that they send to the system operator. There's 10,000 wholesale customer bidding for demand, and then there are traders from banks, from whatever that they make these players make forecasts about tomorrow's prices and take positions with bids themselves. But this information also enters the optimization problem, and then the system is transmission constrained, so with the usual PTDF representation that we've seen, with 9,000, almost 9,000 buses, and then the system operator also has to worry about if stuff fails. The bottom line is that this is an enormous optimization problem, and it's a hard one to solve because there is one feature about this problem that we haven't encountered so far in the course. Day-ahead unit commitment decisions are about starting a unit up or not. Well, with the exception of what Jean-Francois mentioned about storage levels, where that's a continuous decision. As far as thermal generators are concerned, the decision is, should I start the unit for tomorrow or not? Why is that a hard decision computationally? How would you describe that if you wrote a math program for it? Maybe I make a forecast for renewables, so I don't care about uncertainty anymore. This is my demand forecast and my renewables forecast, but it's still a hard problem. What is it that, how do you describe an on-off decision in mathematical programming? You have a binary variable. And you have thousands of generators with binary variables, and you have to decide to make a decision for every hour, for every generator. So that's a lot of binary variables. Now, as solvers develop, so does the control room. So back in the, before we even had fancy optimization solvers, people did very simple rules of thumb, like the merit order dispatch that we saw in the first course, I think, where you stack generators in terms of increasing marginal cost, and you dispatch them in that order unless you violate some transmission constraint, in which case you redispatch, but it was very ad hoc. Of course, in reality, if you do that, you're probably going to be suboptimal, because maybe a generator has an extremely low marginal cost, but a very high startup cost. In which case, if you use that rule of thumb, you're not doing the smartest thing possible. But given the computational resources back then, it was the best people could do. And around the 70s and 80s, when computers started getting into the game, techniques based on Lagrange relaxation were used, combined with dynamic programming. So in particular, people did a Lagrange relaxation on the power balance constraint, which decomposed the problem per generator. For those of you that have taken 2491, composition should sound like a familiar notion, and we're also going to cover it in this course, so we'll see this in action. And so that way they could break up the problem in smaller pieces and solve it in a more intelligent way. And over the last few years, there have been amazing achievements with branch and bound solvers. So the size of mixed integer linear programs that we can solve these days is enormous. It's much, much larger than what we used to do a few years ago. So these branch and bound solvers have made their way into the control room. So now we're using branch and bound for unit commitment. And so let's look at what and you'll be asked for the next homework to actually formulate such a problem, solve it in a small system. And so let's see what the model looks like. The first thing to notice is that there's a time dimension now. We're doing a multi-period optimization problem with a horizon of 24 hours to 36 hours. So we're looking down the line 1 day to 3 days ahead. Now, the objective function is, again, maximizing welfare. So consumer benefit minus generator cost. Why do you think these two terms look different, though? What property does this function? I'm expressing here benefit in terms of hourly benefit, whereas here I'm not doing that. Why do you think that's the case?
Because the generator can change from an hour to another its production.
It can change it.
The more constraints that you have to, you can shut it down, and but you can't activate it the way you want.
Right, so there are constraints that limit what you can do, and it depends on the past. Those could be in here, though. What is also the case.
Yes.
Exactly. So the objective, the cost function itself, if you told me what you did each hour, and only that hour, and I could turn around to you and say, okay, if you did that for that hour, it cost that much. You can't express the cost function in that way. It's not time separable. You have to also tell me what you did the hour before, so I know if you started up or not. So it's a non-separable overtime function. I need to know the full sequence of commitment and production decisions so that I can tell you what the cost is of what you did. Is that clear? Whereas for the consumers, if you tell me how much you consumed for that hour, I can tell you what your benefit was for that hour. We'll see that now in a specific example. Okay, so that's another thing to notice here about the separability. Now, this is what makes things difficult, is the unit commitment decision is a 0-1 decision. So what we're deciding specifically is for generator G, for hour T, Is it 0, which means off, or is it 1, which means on? Then the production, consumption, and power flow variables are the way we've seen them for the optimal power, for the economic dispatch problem, non-negative variables. We also have a net injection for each bus. And this is a generic set that represents the constraints. We'll see them in detail, and that's all to discuss about this slide over here. Now, here's the reason why the cost function is not separable from time period to time period. There is the startup cost. So, if you just told me what you did for that hour, I wouldn't know if you started up the hour before. So to tell you how much your actions cost, you need to tell me what you did for the full horizon. So what do you understand? So I'm telling you, this is a startup decision variable. It's 1 if you went from 0 to 1 in hour t, and it's a 0 variable otherwise. So what do you understand these? What do you understand this cost function as? What are you paying for here in terms of running the generator?
You pay for the fuel, you pay for the starting.
Fuel startup.
That's one.
And that's a minimum load cost. So every hour you want to be running your units, you pay for various reasons. There's extra fuel you need to be throwing into the generator on top of the fuel you need for electricity production. There is crew costs. So this is the running cost that you pay every hour. The load benefit is the usual expression we've seen. And here's the startup decision variable. So this will also be a binary decision variable in our model, and we will want to build up equations such that whenever the previous commitment was 0 and the current commitment is 1, this v variable becomes 1, and we will want it to be 0 otherwise. Okay. And now, I'm assuming a constant marginal fuel cost, but we can get much more fancy about this and describe non-linear fuel costs for each generator, and there are models out there. The important thing is that the models are linear. So even though they're very detailed, you can get away with a mixed integer linear program, which means that you can then use branch and bound, which is great because the solvers are so strong. But we won't look at that in this lecture. So there's the startup cost and the commitment cost that we pay every hour. Now also the startup, you can have a much more detailed model about how a unit starts up, but we won't see that in this lecture either. Now, the constraints that the unit commitment problem has that don't change compared to what you've seen so far are the power flow constraints. So net injection is again at each bus production minus demand, the energy balance constraints, the flow as a function of injection through the PDBFs, thermal limits on the flows, and the demand dispatch constraints. And so these are the same as what you've seen already in the economic dispatch problem. The only thing that changes is that you have one for each hour now. Okay. And these are the constraints that are slightly different. So what do you understand is going on here? This is a P-min, which is the minimum level of production a unit can have, and this is a P-max, the maximum level of production. So how do you understand these two constraints here?
If your unit is on, so UGT is equal to 1, then your production must be higher than the minimum.
Mm-hmm.
So P min G times 1 is lower than the production.
Right.
And if it's off, then there is no constraint about the minimum production because it will be 0. And then you get it in the second constraint where you then have the production is lower than 0. And if it's on, you also get that the production is lower than the maximum allowed production.
Exactly. So when you're on, you can play anywhere within your P-min and your P-max. But if you're off, you have to go to 0. Yeah.
The second condition isn't very necessary.
Here?
If it's off.
Oh, here.
Yeah. If it's off, it will be less than G
So you're proposing we ignore the second constraint?
No, but there is
plus.
nothing
Right,
explicit.
PGT less or equal than
P plus G.
No, because then there's nothing that is impose PGT being 0 when your unit is off.
But it will be
The program, no, your maximization program is then gonna set UG to 0 because it will bring cost in the optimization function, and it will set the production to high amounts, and that's not in contradiction with your model.
You see what it's saying? Suppose you ignore it. He's saying that the optimal solution will always have u equal to 0. The reason is the objective function. You're paying for it. You should be paying for it. So what Benoit is saying is if you don't have this here, you can have 0, you can produce up to that level, but you get it for free, which is not what we want.
so that's a condition for UGT, but not okay. I understood.
The bottom line is you need something like this to show up in your math program, otherwise you don't capture the effect. Okay, so how about here? What's going on here? This is one of the constraints that creates intertemporal dependencies now. So what do you understand with this constraint?
Ramp rate, this is the time required to switch from off to on?
No. If you're on, how fast you can go up.
Oh,
Megawatts per minute that you can move up or down. There's both of these constraints. That's why it's important to do day-ahead planning, because if my forecast is that I will be over here, but my unit can only go up at this rate, I won't be feasible. I need to make sure that by this hour, I'm at least over here. This is the time dependency that creates these complications that make day-ahead planning necessary. This is one example of the time dependency. Is this clear? Yeah? Okay. Now these are a bit more tricky, but don't worry. We're going to understand them. These are called the minimum up and down time constraints. The first constraint here says if you turn the unit on, you need to leave it on for 8 hours, for example. And the reason that's true in terms of like the mechanical engineering of the units is that you can't. You need to have the unit spend some time in a stable state before you can shut it down again. You can't be turning it on and off like crazy. These things break or it costs too much to do it. So how does this constraint capture this effect? What's the logical implication that we want to capture? So we want something like this, right? If VGT is 1, what do we want as a consequence of this in our model? If VGT is 1, what would we like, given that this is the constraint I'm telling you, that once a unit turns on, it has to stay on for at least UT hours. So what would we like as an implication of this in our model?
The next VGTs for T going from period time previous there will be zero solution.
So you're saying that if I start now, I want to not start again.
Yeah, but it's not enough because you can close it and start it. So
That's not enough. Really what you want to capture is that if I decide startup now, I will be on for the next UT hours.
so you
VG lower or equal than VG plus
no equal to 1.
Equal to 1.
for P.
If VGT is 1, I want to make sure that UG T plus 1 up to T plus uptime is 1. That's what I want to make sure happens. Now, this constraint will do that for you. So notice what's going on here. Let's see it. So what happens? Let's look at time period T. What happened? So I'm fixing now the T. Okay. Suppose that VGT is, so what's going on here in terms of, if you think of this summation, is we have a certain, so looking at the time axis, we have a certain time T, we have a certain UGT here, and we are summing up a bunch of VGTs before it, up to time T minus UT plus 1. So we're summing up so we're saying that this guy will be greater than or equal to all these V, well, to write it out explicitly, VG T minus 1 up to VG T minus whatever, this stuff here. So I'm looking at UGT now and summing up all the V's that preceded 8 of them, if it's 8 hours of startup, and I'm making those a lower bound for this variable, right? That's what's going on here. I'm looking at all the V's before it. If it's 8 hours, I'm looking at 8 previous V's, summing them up, and putting that as a lower bound to U. So if any of these guys is 1, what will happen with the U? You're saying that if any of these guys is 1, right, the U's will be 1. This inequality on its own is not enough to do that. This inequality on its own will make the UGT be at least 1. And since it's a binary variable, it will be exactly 1. But this inequality is then repeated for every time period. So if the V that is on is here, it'll show up in this inequality. And that goes also backwards. So it'll show up repeatedly and it will be forcing the U's to be 1 for UT hours moving ahead. Do you buy that, Benoit? You look a bit puzzled. And we can do a specific example. So suppose I have a startup time of 2 hours, or let's say 3 hours. Suppose I have a minimum uptime of 3 hours, and I start up the unit at hour 1. Okay, what is this constraint going to look like for hour 2? UG2 greater than or equal to and uptime of 3 hours, and we're at T equals 2. And let's say I'm at T equals 5 because there are some boundary effects there. So we are at T equals 5 and the uptime is 3 hours. What is the UG, what is this constraint going to look like over here with the right hand side of UG5? It's a summation running from what to what? From 2 to 4. I told you that this is 5. 3 to 5. We agree? Okay. So if I have VG of 3 equal to 1, UG5 is affected. Has to be 1, right? But then this constraint will repeat itself. It will show up also from 46 VG tau less than or equal to UG6. So UG6 will also be forced to be 1 because, no, sorry.
I thought UG was binary. It's not binary, it's discrete. UG is not 1 or 0, it can be.
UG, it is. It is binary. We define it when we write out the math program as binary. Here.
How come it's not the constraint cannot be like a 3 less or equal to UG?
Well, I agree with you. So if all of these v's are 1, then that would violate this being binary, which means that since this will be described in my math program as binary, not all of these can be 1. At most, one of them can be 1. You agree with that? Yeah? But the fact that I've defined it as binary doesn't contradict this constraint. So now I screwed up, I think. Yeah.
You won't have more than one VGT that will, or VGT that will be 1, because if it's on, it's on for a certain period, so it's not on and off again, so VG, there is only one that can, VG that can be 1.
I fully agree with you. I fully agree with you. Also, what I wanted us to notice here is that, well, I kind of screwed this up. So I should have actually written here from 2 to 4, UG4 will be, we will also have this constraint, and here, among these guys, is also VG3 equal to 1. So, in that case, UG4 will also be pushed to 1. And finally, UG3 will be greater than or equal to sum from 1 to 3 of VG tau. And because VG3 will be 1, it will also show up in this left-hand side, and it will push UG3 to 1. So you get exactly what you wanted to get. If you decide VG3 1, it will push the 3rd hour, 4th hour, and 5th hour commitment to 1. And only those, okay? And like you said, it will also force the other V's to be 0, which is completely fine. I mean, if we're starting up the unit at period 3, we only wanted to start at period 3. So what I've shown you, basically, is that this inequality gives us the implication we wanted. Now, you also want to make sure that it doesn't cut off other feasible solutions. This is an inequality that I'm throwing to my math program. So, if you think in terms of integer programming, and I'm going to make this a bit abstract now. If you think in terms of the lattice of feasible, I'm just going to draw the lattice for 2 variables here to try and illustrate my point. So there is, this might be a good example in fact. So okay, here, let's think of what combinations of these 2 variables are feasible for our problem. And if V is 1, I know U has to be 1. So this point is feasible. Because if I start up in hour 1, the commitment for hour 1 has to be 1. Right? So this is a feasible point. Would this be a feasible point? Here. For our problem? No. Cannot be. So, also, could this be a feasible point? Why do you think not?
Because if it starts in time, I don't know, 1, you
So what I'm describing here, you are right. So if it starts at 1, the u has to be 1. So why then is this, sorry, okay, you're right. Why then is this not feasible?
Because it is not started, so you cannot.
I haven't talked about boundary conditions, but it's possible that it was up the last hour of the previous day. So this could be a feasible point. Also, this could be a feasible point. That hour for the specific unit, maybe it was off and we also didn't start it. So these guys are, so we said this one is not, okay, so these guys are okay, and this one is not okay. This is, in this lattice, these 3 integer points are feasible for our problem. Now, extend this to multiple dimensions, so think of the combinations of feasible integer points ranging from UG1 to UG24, because that's the total number of integer variables we're looking at for our problem, and also VG1 to VG24. That's a 24 times 24 dimensional space, which I can't draw on this board. But you can see how some of the points in this space are feasible, some are not, right? In integer programming, when we're solving an integer program, we want to come up with, so these inequalities here define cuts in this space. The best possible cuts you can, the way integer programs are solved is by relaxing them and taking linear programming relaxations. Whatever cuts you define for your space, you want to make sure they cut off infeasible points, but include all of the integer feasible points in them. And then you send this as a feasible solution of a linear program to your solver. And what would be the best possible, suppose this is the only space we're working with, what would be the best possible cuts for this set here? The tightest possible. Come again? Right, so you wanna include the 3 points as the convex one, exactly, of this space. So one cut would be this here, the other would be this here, and the third would be this here. So this is the tightest region you could send as a linear programming relaxation to solve the integer, the unit minimum problem. Turns out that these minimum up and down time cuts do define the convex hull for the up-down time constraints. So they're as tight as possible. In particular, they won't cut off any feasible schedules. But in terms of a linear programming relaxation, they're as tight as possible. And that's something that was proven by Samar Takriti and Deepak Rajan. Okay, now, not that you need to worry about knowing any of this stuff about integer programming for the class, it's just I'm trying to explain that these are really smart ways to write out the minimum up and down times. As far as the minimum downtime is concerned, we have a similar looking constraint. The implication that we want to have hold in minimum downtimes is that if I shut the unit off, I want it to stay off for dt hours. So if I was on in t-1, then I shut off, I want to make sure that for period t+1 up to t plus downtime, I stay off. Okay? The way to write that out is this constraint here. Similar analysis. And then what does this do? Could we get away with our model with not having this constraint? What do you think it's doing for us?
It just means that if you turn it on, if it was off at the time t-1 and now it's on, you have to turn it on.
Right. And so it's pushing the V to 1. Without it, the V would never become 1. We need this constraint in there. Okay, also if it's off for both periods, that's fine, V can be 0. Okay, so that's minimum up and down. Okay, so these constraints now make day-ahead planning really important because some units need 8 hours, 10 hours, 16 hours of downtime, for example. So if I shut it down today, Thursday, I know that until the beginning of Friday, the unit needs to be off. So that's a very long constraint, so that's why I need to be planning down the line, looking deeper in time. So these are another example of constraints that create temporal dependencies. Okay, and like, yeah?
Why is it 1 day ahead? And why do you plan 1 day and not 2 days? Or
so it runs from 1 to 3 days, typically. And it's not commonly necessary to go beyond 3 days because any constraint that I decided about today evaporates 3 days down the line. If I have a minimum uptime of 8 hours, how deep in time will my decision now affect my life? Can it affect my life 1 week down the line? It's an 8-hour constraint. Come again?
16 hours.
Right.
If
So,
it was on, you need 8 hours sitting there, and 8 hours sitting there.
so it's an order of magnitude of the time coupling that is created. So that's why when you're doing day-ahead unit commitment, you don't solve a 1-year problem because 365 days from now, it doesn't really matter what you decided a year ahead. Okay, so that's why the horizon is typically 24 to 36 hours. Of course, the deeper the horizon, the better decisions you make because you're accounting for what you know.
But it's also harder to predict.
But it's harder to predict what's going to happen, and also some things just don't matter for 4 days from now. That's the idea. Okay, so this is a bunch of details you can add to the model. And I've been working on some of these. Pierre-Antoine Absir has been working on some of these we're both inspired from problems that GDF Suez has. So you can have startup costs that depend, the cost itself depends on how many hours have gone by since you last started up your unit. That's tricky to model as a linear program if you think about it. There are ways to do it as a mixed integer linear program. There are papers out there, and we're doing some of these implementations ourselves for GDF Suez. Then you can have a nonlinear heat rate curve. Again, you can get away with a linear model. The ramp rates can depend on how much you're producing, and there are sometimes these predefined sequences. So if I decide to start up now, then for the hour t plus 1, so if I decide to start up now, for hour t plus 1 I have to produce in this level, for hour t plus 2 I have to produce in this level, and for hour t plus 3 I enter generator minimum. And I then am playing in this phase here. But up until t plus 3 hours I follow the predefined startup sequence. We did an interesting project for Colombia where we were trying to predict market prices based on their hydrothermal fleet there, and you really need to account for these details to understand why the prices are what they are. So once this generator enters this dispatchable region, it starts influencing the market price, but before it enters it, it can't touch the price. So accounting for these constraints really matters for the project. So there's a lot of applied stuff you can do with these models. It's really interesting area of work, I think. Okay, I think we're good for a break. No, we have 15. Okay, yeah, let's do a bit of the reserve requirements and then we'll take a break. Okay, so one of the reasons that, yeah, Okay, so one of the reasons these models are so interesting is because there's a lot of output coming from them that is useful. I haven't shown it to you yet, and we're going to do it now, but you can also throw in reserve constraints in these models. So these models will tell you if this is how much reserve you want, this is how much it will cost you to get it. So you can do a cost-benefit analysis of putting more reserves into the network and how much it's going to cost. The operating cost itself is something that we explicitly compute in the objective function. And then how much renewable energy or conventional thermal energy we use is one of the decision variables of the problem. So the output of these models is very interesting for policy support. For example, when we are throwing in, why don't we just use wind power to get over the whole energy problem? That, for me, that was the idea of my thesis, and the motivation of the work I did is, okay, in an ideal future, we just only use wind power, for example, in electricity systems. But what is it that, what are the problems that are caused by wind power, for example? Yeah, I mean, I can't depend on turning on my TV after 10 hours of work on whether it's going to be windy in Belgium to watch TV, for example. So, so if you want to use a lot of wind, the good thing is free fuel. You don't pay for wind; it's renewable. But you need reserves there in case it's not around. Well, a model like this will tell you how many reserves you need. And so uncertain production makes this model really interesting. It helps you analyze a lot of trade-offs, so that's what we're going to discuss next. So there are 3 different philosophies that I'm going to show you today for accounting for uncertainty in these models. The first is a deterministic model for reserves, where we tell the model how many reserves we want, and the model says, okay, if this is the amount of reserves you want for each hour, this is how you should commit your units. So we saw the unit commitment problem. Now we're going to also add reserve requirements to the model. And to do that, we're going to define 2 variables. One is spinning reserve that can be offered by units that are online, and non-spinning reserve, like we saw in the last lecture, by units that can be offered also by units that are offline. And the twist we add to the model is we tell the model, okay, I want for each hour of the day a minimum level of total reserve. And if you want to think of this in terms of the picture, I drew this also last week and I added it to the notes. Maybe it's not like that this way. If you want to think in terms of a picture over the day, if this is your P max and your P min, and this is how much you've decided to produce for that hour, the amount of reserves that is available is this. The amount of spinning reserve that is available is this space here. So you are looking now for a schedule that each unit needs to obey in terms of electricity production, but you also want to create enough space, and the sum of overall generators of this space that you have to move has to be above this level here. Also, you can add non-spinning reserve requirements, so even units that are off can contribute to reserves. The way to model this is for this space here, you add the spinning reserve decision variable. It's a non-negative variable, and you say that the sum overall generators of the spinning reserve they can offer, so this the space I need to let free, has to be above the spinning reserve requirement level, and the same for total requirement. Okay, and here's how we modify the constraints. So, how do you understand this constraint here? Does it make sense to you?
What's the difference between spinning and non-spinning? It's S and N.
Spinning and non-spinning. So what is this constraint saying?
It's the largest amount of production you can have.
It makes sense that if you can only produce 100 megawatts, you can't promise to produce more than 100. But also, if you want to offer spin and non-spin, you can't go above your P max. So your emergency production plus your promised production of P can't go above your P max. That's the idea here. But what makes the two different, spin and non-spin, in these constraints?
Spin comes from units that are already on, so
right. So this constraint here makes them really different. If you don't turn your unit on, so this is 0, then you're stuck with a spin of 0 and a production of 0, of course. But you can still offer non-spin, even if you're off. And then this ramping constraint now says that if you promise me emergency ramp up, emergency spin, you need, and you've also promised me an increase in production, the combination of the two has to respect your ramp rates. So this is how we model reserve requirements. And the first, I think the second exercise in your home, oh no, I didn't add this. Oh, okay. Yeah, it's not in your home. This is not in your home. Okay, and now we also have these import constraints that they're another way to protect the system against outages. And the best way to describe this is in terms of a drawing. So this is a typical situation. For example, in San Diego, it was a classic import constraint that was, San Diego is a large city in California. So the thing there is that they have a local load. They have a bunch of lines that bring electricity into San Diego. So San Diego here is the B1 node. They have some local generation, and the rest of the power comes from outside. These arrows don't indicate direction of flow of power, they just indicate the reference direction in my graph that defines my electric power system. So if I'm writing the model in ample, this is just saying that the from bus of line K, so I define a bunch of lines as a set in ample, and the parameter from bus that indicates line K1, what is the from node, and the to node. That's a way for defining a directed bus in ample. So the from bus of line K1 is B3, and the to bus is line B1. It doesn't necessarily indicate the direction of the power flow. So the situation with San Diego was that if a generator fails in San Diego because it is a load pocket, we know, based on operator experience, we will need to bring the power from outside. So what would happen if in normal operation I committed my system in a way that these two lines that are bringing electricity into San Diego are at their maximum limit, and then the generator fails? What would you have to do? Suppose that these two lines that are bringing electricity into the load pockets are at their limits, and suddenly your generator fails in here. What's your only option to balance the system? You lose local load. That's the only way you can get yourself out of this imbalance. Well, you definitely don't want to do that for large city centers, so you leave some space open in these two lines. So you say that the sum of power flowing here and here has to be less than or equal to a certain limit, so that if this guy fails, I can increase the power that's coming from outside. Okay, so these are called import constraints. They're another way of protecting your system against disturbances. So in particular here, if we wanted to impose an import constraint, we would have to have a constraint like this. And why am I using the minus here for K2? The reference direction. So a negative F, in fact, in this model means that I'm bringing power from B2 to B1. So this is really the constraint I'm asking for is that I don't want more than 100 megawatts flowing over these two lines. So the total flow over both of these lines can't go above that limit. In case something goes wrong, I can bring power from the outside. So to define this, we use these import constraints. So we define an import group which consists of these two lines. And the import constraint is 100 megawatts. And we also define the reference directions, which are the coefficients here, 1 and -1. And we impose this import constraint. We say that the total amount of power flowing over these sensitive lines can't go above the import constraint limit. And that's another way of protecting the system against bad things. Okay. Okay, this should be in an earlier slide. So this is initial conditions. I talked about them briefly. I'm going to jump over this in order not to interrupt the discussion. I'll fix that in the presentation. Okay, so one criticism about these models, and actually what I just showed you, the unit commitment problem plus these tricks, is the standard way for running systems currently. Recently, people have started criticizing this. The reason being that up to now, these rules have worked well with a low demand uncertainty, but in systems with enormous uncertainty because of, for example, renewable energy, these rules are a bit too simple. You can apply them and you're going to commit reserves in a certain way, but you're not being smart enough about how you represent the uncertainty, and the resulting unit commitment schedules kind of suck. So there's been a lot of work on improving the model that we use for protecting the system against uncertainty. In the reserve requirement model, the total and the spinning reserve requirements are numbers that the operator just comes up with based on experience. They're going to have a huge impact on the resulting unit commitment, but they're basically, you pull them out of your pocket based on experience. And for the import constraints, what import groups do you want? What should be the lines on each import group, and what should be the flow limit? These are again based on heuristics. So that brings us to alternative models for optimizing unit commitment under uncertainty, and we can see them in more detail after the break. So the new model would look something like this for the generator failures. If for that scenario I lose a unit, I create my data in such a way that I push the Pmax and the Pmin to 0. That forces the production to be 0. Now, there's stochastic unit commitment model has a bunch of structure basically. So that's one of the tricks you can do to model uncertainty. Push the Pmax and the Pmin to 0. So what do we need to define to build up these scenarios? First of all, you need to define a set of scenarios in your code, and you need to assign a certain probability to each of these scenarios. And the objective of the model will be to optimize expected cost. So this was a trick for modeling generator failures. And we can do a similar trick for modeling wind production. So I will split now my group of generators between conventional units that I need to do unit commitment for and renewable units. And for the renewable units, I will have an hourly production that depends on the scenario. That is a way to represent wind production, for example. You have different profiles of wind production throughout the day. So for each hour of the day, you have a time series that describes a possible evolution of wind production. And these are the PGST parameters for G that are renewable. And this is what your objective function will look like. So we're doing expected cost optimization. we're weighing each scenario by its probability, and then we're solving this problem here. So there's two types of decision variables in this problem. We have unit commitment decision variables and dispatch variables. These don't have an index over scenarios, and these do. How do you understand the fact that I'm not indexing these over scenario? How do you interpret that?
You don't know which scenario is going to happen before, and you have to take a decision what you're going to do, whatever the scenario that is happening.
Exactly. So the sequence of events here is I decide the day before, then I get to see wind and what units failed, and then these are very different decisions now. Now I've seen what happened and I can balance the rest of the system. That's the idea of the model. All the while, I'm trying to optimize expected cost. But like Benoit said, these are basically first stage decisions. So this is basically a two-stage stochastic program that we're looking at. And so here's a couple of questions for you. What's the harm of committing a lot of? Why don't I just commit all the generators in the day ahead? It's the safest thing I can do.
Because then you have to use them, you have to pay.
What specifically hurts you when you commit all of them? If you remember the objective, the cost function, the generators, there were three pieces to it. Mid-load cost, startup cost, and fuel cost. If you start them all up, you pay for all of them a startup cost, and you're running them all the day, so you're also paying mid-load costs. These can be very substantial. So it's not necessarily the smartest thing to do to start everything up and have it running for the full day, and have everyone running really low. Also, if we had a more detailed description of the fuel cost, you would see that if you run a generator really low, it's very inefficient, whereas if you bring it closer to its maximum, it's the peak efficiency that you can get. But on the other hand, why don't you want to do the opposite?
Because then you have to satisfy everything.
Yeah, you run a high risk of losing time. So there's this spectrum of things you can do, and the two ends of the spectrum are really stupid decisions, and somewhere in the middle is a good decision to make. That's what the stochastic commitment model helps you do. So this is really the trade-off we are optimizing. And all these constraints, you saw them identically earlier. So these are the power flow equations. The only thing that has changed from the vanilla unit commitment model is that now we have scenarios. So these are second stage decisions. And so net injections, power, energy balance, and the flow definition, thermal limits. Here's the trick I showed you for modeling the failure of conventional units. You push these two parameters to zero, and that forces the production for that generator to zero. And for the full day, if the P plus and the P minus are zero, the PGST is zero for all the T's. And for the renewable production, we have this thing here that says that the maximum production I can get for that unit is limited by the scenario. Now, for renewable units, I don't have unit commitment decisions. Okay, they're there. I don't have to start them on. It's not a decision I have to make one day in advance. If I get the power, I can use it. Also, there's no fuel cost for these units. You're only paying fuel cost for the conventional units. And then ramp rates are like before. We don't have reserve requirements in this model. So the reserve decision variables, we throw them away. Basically, building scenarios is another way of doing the same thing as reserve requirements, just more detailed. And this is for demand forecast uncertainty. Now, can you think of a couple of reasons why this model would not be used in practice? it looks like a very detailed model. So what can you identify as possible difficulties? Think in terms of from beginning to end, from building up the data to actually solving it. Yeah, that's just weird. I mean, and it also matters a lot for what will happen. So that's one thing. Then the time series models for the wind production. So building this data is difficult, possibly, and also the size of the problem can become very large. When I was so for my PhD work, I ran the California reduced system. One scenario runs in maybe 3-4 minutes. 10 scenarios for the same system, about 16 hours. 1,000 scenarios in a supercomputer with 1,000 machines needs about 3 days. So these things, because you're using branch and bound to solve it, you're increasing the number of integer decision variables linearly with the number of scenarios, but the combinations of things that you could decide explode. So it's a difficult problem to solve. And so this is some of the criticism that stochastic unit commitment has been receiving. Whereas the deterministic unit commitment with reserve requirements, which is solved by industry today, you can solve it within fast enough to use it in a control room. So that's why it's used today, even though it's not the most intelligent thing you can do. Okay, and the last version of reserve requirements that I wanted to talk to you about is security constrained unit commitment. So here the idea is to, first of all, in these types of models, the demand is not flexible. We have to satisfy all of it. So load sharing demand is not an option. It's an infeasible decision. Which means that in the power balance constraints, the little d decisions are replaced by the actual full value of demand. There's no backing demand down from their block bit. So again, we have conventional and renewable generators. Now, the philosophy in these models is that I want to make sure I minimize the cost of operations in case everything goes as expected. So the 0 here indexes a no contingency situation where everything goes fine. But in the constraints, I'm gonna add scenarios where I only use one element at a time. So I will only have these constraints here, but only losing one element at a time. In a general stochastic program, I can be losing many of these in a single scenario. In a security constraint model, I'm optimizing cost, assuming everything goes fine, but I want to make sure I commit in such a way that if I lose any one generator, I will satisfy all the demand. This is a classic way for planning, practical planning in power systems. For example, in France, which relies on nuclear, or in California, it's the same thing. The amount of reserves we plan for is the largest unit in the network, which is a large nuclear unit. If we lose that nuclear unit, we are screwed, so we want to make sure that the reserves that we have online can make up for that on time. So usually, this is very consistent with what operators do in practice. But it's more conservative, again, compared to a stochastic unit commitment, and if you want to solve it in its full complexity, it can be quite large. Any questions about unit commitment? You'll implement a couple of these on a small model, and for the project, I'm thinking of a project on stochastic unit commitment. So you'll get a first taste from the homework that's coming up next week. Does this look understandable? Now, I would like to place some emphasis on solving the actual problem. So for those of you who have been taking, well, that would actually only be you. 2491, we did Lagrange relaxation, which is the approach for solving the stochastic unit commitment model. So next lecture, I'm going to talk about subgradient methods in Lagrange relaxation. Okay, so the last thing I want to talk about, as far as optimal power flow is concerned, is if you remember in locational marginal pricing, we have a different price for each different bus. And I showed you this color map a few weeks ago of the PJM market, I think it was, where you had thousands of prices, basically. You had a whole color map which corresponded to a different price for electricity. So one of the criticisms people, and this is actually a real market being cleared every 5 minutes with thousands of different prices for each area. So one of the criticisms people raised against locational marginal pricing is that it's a bit too complicated, there's too many prices, there's too many electricity products, and actually you can exercise market power because you're splitting a huge market into many small markets, and if a player has a lot of generation in any one of these pockets, they can play games and manipulate the prices. So an alternative idea was to group up many nodes into zones and just have fewer prices of larger groups of areas, which led to this whole debate about what is better. Should we do nodal pricing, very detailed for each location, or should we group up, create fewer markets but more liquid markets with more players in each market, which is zonal pricing. Now, that's how many markets were originally designed. So California was set up like that. In the beginning it was north-south, and there was this one path that was constantly congested, so that was causing a lot of problems. Eventually it split into 70 different zones. Nord Pool was and still is organized as a zonal market. PJM, on the other hand, what we saw in the color map is nodal pricing. And in Europe, we do a lot of things according to the zonal paradigm, where basically each country has its own price for electricity throughout the whole country. So a whole country acts like a zone. And so when you're designing a zonal market, you're basically approximating reality. And that causes problems. And you're taking what is the physical description of a real power system, and you're trying to replicate the power flow equations on an aggregated network. So one of the questions that comes up is, okay, how many zones do you want to create? Which buses are you going to put in which zones? And now that you have a reduced network, what are the PTDFs for this aggregated thing that you're defining? And this creates a departure from reality, and that causes problems. Now, implicitly, one of the things you're doing when you're collecting many nodes is if I have this network and I say I want to create a north zone and a south zone. So when I try to draw this now as a network, with only 2 areas, I have something like this. North zone, south zone. One of the questions is, how much is this capacity? Then an implicit assumption here, if this area is going to have a single price, it means that there is no congestion within the area, which in reality is not true. If you dispatch the system assuming a single price and that there is no congestion in this area, the actual dispatch decision you make might actually be violating what's really going on within the area. You might actually really have congestion. So we'll see this specific topology in an example, and you'll see how zone pricing can become problematic. So here's the 6-node example that I've just drawn on the board, and you just have these 2 lines here that are congested. So line 16 has 200 megawatts of capacity, line 25 is 250, and node 6 is the hub. I'm giving you the PTFs for each of the lines with respect to 5 nodes, except for the hub node. And I'm also giving you data on the cost curves and the benefit curves of each bus. And marginal cost curve. So if in bus I have a load, the BI is positive, and it has an increasing marginal cost curve. If bus I is a generator, the BI is positive, and I have an increasing marginal cost curve. If bus I is a load, BI is negative, and I have a decreasing marginal benefit curve. Okay. How much, suppose that I broadcast a price lambda I in bus I. How much would it, and suppose that I have a generator located in that bus, how much would they want to produce for that price? So let's take the first let's take bus 1 for example. We have a marginal cost of 10 plus 0.05 Q, and I'm paying you lambda. How much are you going to produce? Again, if you remember the logic of, in this really simple model, there's no unit commitment or anything. So, if this is my marginal cost, what's the optimal thing for me to do?
Equal the marginal cost to lambda.
Come again?
Equal the marginal cost to lambda.
Right. So I'm going to go up to my marginal cost. So, if I give here a value of 9, then how much am I going to produce? I'm going to go with 0, right? It's not high enough to start me up. So the plus operator here is just, this just means, yeah, positive part of the equation, like max of this and 0. Same idea for the loads. So I'm gonna increase marginal consumption up to the point where my marginal benefit is lower than the price that I need to pay. So the same formula, in fact, applies for the load. And so the flow that I get on each bus. And now suppose that I define this whole thing as a single zone. I want to forget about locational pricing. I just want to simplify things and run this as an economic dispatch auction like we saw in lecture 1, single price for everyone. The reaction of everyone to this single price would be this here. And the actual flow on line 16 would be given by injection times PTDF. Okay, are we comfortable with the constraint here? So I told you that 2.5 has a limit of 250 megawatts. Sorry, 1.6 has a limit of 200 megawatts. Let's see. Let's start from a really low price and go up to a really high price. See at what point this flow will respect the 200 megawatt limit. Okay, I'm giving you the numbers here, so you can plot this in MATLAB as a function of rho. What you get, in fact, is the red line over here. So what's the bad news in the single price? There is no price that will make you clear this market. So if you look at the setup of this example, we have a really low cost unit in node 1, really low cost unit in node 2, and a pretty expensive unit in node 4. So 1, 2, and 4. 1 and 2 are going to start producing first. They are the cheapest generators out there. And you have a really eager, so to speak, loads in 5 and 6. The A parameter means the first slice they bid, how high it is. So the higher the A, the more eager they are. So they're the first consumers to come online. And they're located in 5 and 6, which is over here. So as you start from a really low price, you're just shifting power from north to south, and it's already violating the thermal limits here. Now, to counter that, to make up for that flow and reach a point where you're respecting these thermal limits, you need to wake up generator 5 and create a counterflow. So you really need this price to go up higher. But the moment you do that, these guys start, so the moment you go up with your price, this thermal limit is still violated for another reason. Let's see. Right, it's a single. Sorry, it's been a few weeks since I saw this slide presentation. Anyway, if you stare at the numbers, you can see that even if you try and activate this generator by jacking up the entire price, somebody pushes back and still the limits are violated. So basically, you can't find the proper price that coordinates everybody to respect these two limits. So running this as a single price area cannot work for the specific thermal line of line 16. So the philosophy has been that, okay, let's do it anyways, see which line burns out, and if there is if there's no violation of any thermal constraint, then we clear the market like that. It works for everybody and for the transmission network. If there is a violation, then let's split the area to two different zones and make sure that these two guys, that are the two ends of the line that would burn, are in different zones. So then we have a different price in each of these two areas, and then we repeat. We resolve with this two-zone model see what happens. Again, if there's another violation, we split further, and that's been one idea of organizing zonal markets. And yeah,
Could it be that, so if you say there is a violation, so there is a alignment burn, you split the,
Like this.
the program in the problem into parts, and then you solve it, and then if you have no problem, you split further.
yeah.
But could it be that the way you splitting it two different ways will in one way it will be immediately solvable, and in the other it will mean you will have to solve to split further.
Absolutely.
So then you first have to try all the possible ways to split before splitting further.
That's one of the criticisms with zonal pricing, is that instead of running the LMP in the first place, which is objectively the physical model of the system, now you start playing around with. So one way I could do this is I could have this be one zone and the rest be another zone. So one of the criticisms about zonal pricing is, okay, how do you then define the zone? If you want to split these two guys in a different area, what are going to be the zones? That's where what the debate has been centered around. Is should we go with something heuristic like this, or should we just go with first principles and do LMP pricing?